Hey everyone, I hope you're doing amazing. I'm Kadan Ukharia, and in this video, I'm going to show you my task as a part of internship at the Sparks Foundation. Now, the objective here is to predict student scores given the number of hours he or she studies. So, we are going to fit a simple linear regression model to make our predictions. So, without any further ado, let's start. Now, simple linear regression is one of the simplest machine learning algorithm to exist. Now, the way it works is, it has first of all at very high level two prerequisites. First of all, we need to only have two variables. You can see I have only two variables, y and x. There is one independent variable and there is one dependent variable. So basically, this variable depends on this x. And the dependent variable should be continuous. That's the name this regression comes from. This y should be continuous. And the relation between y and x should be linear, which is the case here because, of course, in general, if a student studies more, his marks will be more, right? Generally, not every time, but generally. So our idea is to fit a model something like this. We're basically trying to fit a straight line here with the parameters beta 0 and beta 1. This beta 0 is called constant, you might be knowing it, and beta 1 is called coefficient. So the first step is to importing the libraries. Now, the libraries are NumPy for numerical computing, of course, Matplotlib and Seaborn for data visualization, and Pandas for, of course, the de facto data frame to store our data. Now, before we go on to do some actual work, let me introduce the data dictionary. Now, the data dictionary is basically a dictionary that explains the various columns in a dataset. Now, in a dataset, there are basically two columns. First is hours, which is number of study hours per that a student studies, and scores. Scores received by a student in percentage. So these are in percentage values. And then I've imported the dataset using pandas readCSV function. And then I'm trying to explore the dataset. So first I just viewed some of the rows. Then I checked how many entries were there. So it turns out there are 25 entries here. And then I checked the columns furthermore to check if there were any null values or not, but it doesn't seem like there were any null values. Then I basically wanted to see what are the various statistics for my data. So when I do some plotting, I should know where the data is going, or simply just to check if there are any odd values or odd values are present or not. So it turns out that nothing seems wrong here, and we have two numerical columns, hours and scores. And hours is a float 64 and scores 064. So it turns out the percentages are in integer values. Alright, so I guess they are round up. That's what we can infer from here. The scores are in 64 and it can be only present if these percentages are rounded off. Alright, so that's the one inference that we got by describing the dataset. Now we'll of course check the correlation. Now correlation basically says how strongly related two variables are. If a correlation lies between -1 to 1, and if it is closer to -1 or 1, it means there is a strong relationship between two variables. Now if it is positive, it means that as one variable increases, another variable also increases. Now it turns out the correlation between hours and scores is 0.98. So what does it mean is, as it is very close to 1, it means that as we can see here, I made a rect plot here. As hours increases, the scores also increases. Now rect plot is basically tries to fit a linear regression model and its own. So basically I've revealed this secret here. But anyway, there is something more to it also. So we can see the linear correlation is explained by this rect plot. Now we'll extract the input and output variables. So x, that is our number of study hours, we'll extract it, and y, that is our scores. And then I'll directly train the model. Now you might argue that why am I not splitting the dataset? Now the idea behind not doing that is there are only 25 entries. If I split the dataset, it won't do any good. But still what I'll do is I'll perform the k-fold cross validation in the end to settle this debate. Okay, I'll come to the k-fold cross validation in the end. But the decision I'm willing to make here is I'm going to train the model on the every entries, and I'm going to make a new prediction depending on a new value. Okay, so the model gets to learn more because 25 is a very small number. So here I have imported the linear regression class. I created an instance of it and I have fitted the model to my input and output. Alright. And then of course my model is ready. It has learned from this x and y. It has learned the relation between the hours and scores, and now I'll make predictions. Now I'll make a prediction for a student studying for 9.25 hours, and after making the prediction, it turns out that he will get, or she will get 92 0.9, that is nearly 93% if he or she studies for 9.25 hours. Right, now we'll see the coefficient and constant values. So what is the beta 0 and beta 1 basically? So the slope is 9.776 and the intercept is 2.84. Now one way to look at this is, even if a student doesn't study at all, he will at least get 2% marks. Okay, and depending on number of hours, as per unit increase in the hours, the score increase by 9.776. It is the way to read this model. At least the students will get 2.4 marks according to our model, and per unit increase in our hours, the percentage will increase by 9.776. That's what the linear regression model is trying to say. Now let's visualize the model, how it is performing. Now here I visualize the model. Now we can see that it is performing very well. I mean, it's not a overfitting or underfitting like scenario. It's a good fit. Now, of course, we need to judge our model on some metric. So what I'll do is I'll perform k-fold cross validation instead of just relying on that simple split. K can be any number. The way k-fold cross validation works is we split our data into k parts. Now, a fold is a fancy number for a part. So we have here 25 entries, right? So we might let's just say we divide our data into 5 parts. If k value is 5, so 5-fold cross validation will divide the data into 5 parts. You can see here we have divided it into 5 parts, and what we'll do is we will train our model 5 times as k is 5, and at every time we'll change the training and test set. The way it works is, first time when I train the model, that is we call it split 1, we'll take the first fold as a testing data set, and remaining 4 is a training data set. In the second split, or the second try, when I create the model, I'll take the second fold, or we can say second part, as testing data set and remaining a training data set. So basically the idea is we break our training data set into k parts, and we take each and every part as a testing data set and train k different models. That's the idea behind this thing. Now we need to, of course, judge this thing at every time. We need to judge the model on some metric. So the metric I've used is the R square. Now the R square basically explains R square of a model basically tells how much variation in Y that model is able to explain. Okay, I'll come to this in a bit, but I've used the cross-val score function to perform 4-fold cross validation. As you try to increase the value of CV, it will generally not give you good results. For the very simple reason is, you should actually have something substantial in the testing data set. If I just use a CV value 10, for example, it will just lead to, I guess, around 1 or 2 values maximum, in the testing data set. So you need substantial values in testing data set. That's why we tend to take the k value that way, so that split is somewhat substantial. I don't want to keep only one value in test set, because that will affect the score very badly. So I perform the k-fold cross validation, and what does this cross-val score function return is, it returns an array of all the scores at different splits. So it will create a model for this split, it will create a model for this split, and so on. So therefore there will be 4 splits created. So and it will give me an array. Now what I'll do is I'll simply create the mean of the scores and standard deviation. It turns out that on an average, the R square value was 92.779 and standard deviation 2.246. Now what does it mean is, on an average, the R square value of our model is 92 plus minus 2, something like that. Now it is not exactly the accuracy. What does the R square tell us? The R square value 92.779, it implies that our model, or our independent variable, is able to explain more than 90% of the variation in our dependent variable. Now I've written here explain 2 times. I'll change it. Alright, so our model average R square value is 92.7. What means, on an average, we can say that our model is able to explain 90% of variation in our dependent variable scores. Okay, so that's what it means. So that's it. Thank you for watching.